Let's take a look at this image here. What should a good object classification model predict? Some of you might say dog, or just animal, or maybe even German Shepherd. And it turns out that all of these options are indeed correct, since animal, dog, and German Shepherd are from a semantic hierarchy. And pretty much any object is part of a giant semantic hierarchy tree, and a specific semantic hierarchy for an object is therefore just a path from the root to the leaf node corresponding to that object. So going back to our dog example, let's get some inspiration from humans. If Alex tries to classify it, he's pretty confident that it's a dog, but unsure about the exact breed. So in that case, it's probably better for Alex to classify it as just dog instead of something that is wrong, like beagle. It's actually possible that Alex has never seen German Shepherds before, so it's pretty much impossible for him to predict the correct breed. And we can apply the same idea to an artificial classification model where it can decide at what level of the semantic hierarchy to predict. In addition, learning how to predict at different levels of the hierarchy might also help us learn better or more meaningful representations for images, similar to what we saw in class with multitask learning. We have seen before that if you train a classification CNN on a variety of classes, it already appears to learn representations where, let's say, dog and cat are closer together than dog and chair. And dog and cat are essentially the same semantic subtree of animals, while chair is in a different subtree, namely like of furniture. So if we provide the model with the hierarchy information, let's say like for dog, and we also tell the model that it's an animal, and this way we hope to optimize more directly for this property of the representations. So given the motivation we presented, we want to design and learn a model that makes the most fine-grained prediction it is still confident about, and therefore classifies images at different levels of the semantic hierarchy. So just to clarify, the model is only going to predict a single label that's like either fine-grained or coarse-grained. So to illustrate the key idea, a fine label prediction, like German Shepherd, is usually preferred. But if the model is unsure, a correct coarse label, like dog, is better than a wrong fine label, like beagle. And while there has been previous work on hierarchical predictions, we haven't really seen any work where the model itself decides at what level of the hierarchy to predict, and that's essentially our contribution. So the data set we're using is CIFAR 100, which has images from 100 fine classes, which are then organized into 20 coarse classes. So every image has both a fine and a coarse label in this data set. To evaluate our model, we call that we are only using one correct label for each input image. And that correct label is either coarse or the fine label, but not both. So the accuracy on this prediction task is what we refer to as hierarchical accuracy. Great, so let's take a look at our model architectures. So first we start off with a pyramid model, which we use as the baseline. It's essentially a branching model that starts with a shared CNN and then splits into a coarse and a fine branch, which don't share weights. So for an image, it first predicts both coarse and fine labels together with a confidence score on the fine prediction, and then uses a threshold to decide which one of those two, like coarse or fine, to predict. And the model is learned by minimizing both the coarse and a fine cross-entropy loss jointly. So, for example, given this image of a dog, it might be confident enough to predict a dog. But let's say given a meerkat, it might just predict animals since it's not sure about a specific type of animal. And now AJ will talk about our CNN RNN model.